Unit 8 is about acids and bases. Here we have two different definitions for acids and bases. The Arrhenius definition is referring to in an aqueous solution. So in water, it is said that an acid is something that donates H ions. And the Bronsted-Lowry definition is even more general. It just says that an acid is a hydrogen ion donor. We do need to remember that. Let's look at the base definitions, however. A base is a hydrogen ion acceptor, but in water, it produces OH ions. Can you imagine that? If a substance is in water and it accepts hydrogen, so it removes one of the H pluses from water, then what will remain is OH. So the Arrhenius definition limits itself to a watery environment, where the Bronsted-Lowry definition is more broad. Do your best to remember these, but these can be a helpful perspective also. Here is an equation with some generic substances. A is not on the periodic chart. Of course, water, the hydronium ion, and then the remaining A. Can you look at this equation and determine which substance is the acid? Which substance is the proton donor? Which substance starts out with an additional proton and at the end has one fewer proton? Hopefully you would agree it is the HA. That is the acid. We know that because it fulfills the definition of an hydrogen ion donor. Water starts out with 2 hydrogen ions and in the end has 3, so it is the base, the hydrogen ion acceptor. If we were to read this reaction in the reverse direction, then which substance would be the hydrogen ion donor? It can't be the A. It does not have a hydrogen, so it cannot be a donor. This substance is the acid in the reverse direction, and we call it the conjugate acid. And this other substance, which takes a hydrogen ion in the reverse direction, is called the conjugate base. We do want to know how to identify conjugate acids and bases. Next, we want to learn how to write K expressions for reactions with acid. K sub A for acid is called the acid dissociation constant. Remember, a K expression is products over reactants. So the two products are written in the numerator. One reactant is written in the denominator. Do you know why water, the reactant, is not written in the denominator? It's because water is a liquid, and liquids and solids are not included in K expressions, only aqueous and gaseous substances. So let's do a practice problem. Write the dissociation reaction and the Ka expression for each of the following. So HCN is hydrocyanic acid, and if it is in water, then it should dissociate or ionize to form hydrogen ions, because that's what acids do, they're hydrogen donors, and cyanide ions, because that's what will remain, the anion cyanide. Both of these will be aqueous, and that is the reaction. The K expression, Ka, since this is an acid, would then include hydrogen ions, the cyanide ion, and HCN, since all three are aqueous and all three would be raised to their coefficients, which is 1, 1, and 1. You try it for 40B. Is this what you wrote? Hopefully you took one hydrogen off, because that's what acids do. You left the anion slightly more negative because it lost a proton, something positively charged, and you wrote all three substances in a Ka expression with square brackets because they are aqueous. Also, it's a good idea to remove the hydrogen that is connected to the oxygen. It's the one that has the very polar bond. And so the oxygen is very likely to take that electron away from the hydrogen and leave the hydrogen with no electron and just a proton. For this last one, you would remove one of these hydrogens because it is connected to the nitrogen. And remember, a bond between hydrogen and phonon is highly electronegative. So one of these are the ones that would be ionized. Let's talk a little bit about the difference between strong and weak acids. If an acid is strong, that means what? When we put it in water, it will mostly form products. It will largely dissociate. Will the K expression be large or small? Well, if mostly products form, then the numerator will be big in our K expression, and K will be large. The equilibrium lies far to the right. For a weak acid, very little of it will dissociate or ionize in water. And so the numerator will be small, and the equilibrium favors reactants in that case. Here are some graphs to show us the difference. Do you think we should write in this next section for strong acids? Ka is greater than 1 because it favors products, whereas for weak acids, Ka is less than 1 because it favors reactants. Remember, a Ka of 1 would mean the ratio of products and reactants are the same. Equilibrium lies to the right. For every acid that is put in solution, a hydrogen ion will form. The symbol on the right is a generic symbol for acids, and the symbol on the left, of course, is the symbol for hydrogen ions. The anion that's formed is a much weaker base. It's even weaker than water because it came from a strong acid. So the reaction does not really go in the backwards direction because a weak base cannot drive a reaction. And then, of course, we do need to memorize isoproclo, the 7 strong acids. Here are some weak acid facts. Equilibrium, remember, lies to the left. The hydrogen concentration is much, much less than the acid concentration. Very little of the acid produces hydrogen. The anion is a strong base. Whatever comes off and produces the anion can drive the reaction in the backwards direction. And of course, it's all other acids except isoproclo. So anything that starts with an H and isn't strong, we will be looking for things that donate hydrogens. That's how we'll know it's an acid. Here's a sample problem. Can you look at these two beakers and determine which one is the strong acid? Hopefully you said this one, because every anion has separated from a hydrogen ion. It is completely dissociated or completely ionized, where this would be the weak acid. So for the items below, we can easily sort them. A strong acid includes isoproclo, no cloclo, and the rest of these are weak. This last one, by the way, is acetic acid or vinegar. Water is an acid and a base, so it's called amphoteric. And this is a famous reaction between water and itself. When water is in a beaker with itself, does it form ions? It does. And if we're doing a chemical reaction, those ions can interfere with the chemistry. Remember in our calcium lab, we dissolved calcium and hydroxide ions in water, and we did a titration to determine the amount. If we used water, there may have been some excess ions in the solution from the water itself. So it's important that we try to use deionized water or distilled water to make sure that those ions are not in solution and interfering with our calculations. That's one source of error. Let's look closely at the reaction. Water can give a hydrogen to itself and form the following two ions. H3O, that is called hydronium, and OH, that is called hydroxide. When water reacts with itself and produces these two ions, we would say that they should be present in an equal amount, because for every water that splits, there should be one hydroxide for one hydronium. And so these two concentrations multiplied by each other is therefore constant in water. K stands for constant, W stands for water. Please note, H3O is interchangeable with the symbol H because any hydrogen ions that exist in a watery environment will cling to a water molecule. So H3O is just water with hydrogen in it, and we use these two symbols interchangeably. Back to K sub W. It is called the ion product constant for water. The ion product constant for water is 1 times 10 to the negative 14 at 25 degrees Celsius. So that's slightly above room temperature, right? So would you say that slightly above room temperature, water produces a lot of products? It does not, because K is such a small value, times 10 to the negative 14. So very little hydronium and hydroxide are in water, but they do exist. From this information, we can deduce that if the hydrogen ion and hydroxide ion concentration are equal to each other, then the solution is neutral and it's just pure water. But if there's more hydrogen, then the solution is acidic. And if there's more hydroxide, the solution is basic. Multiplying the two gives us 1 times 10 to the negative 14. So we can use this relationship to do the second type of calculation in our homework. The OH concentration, and of course K sub W is a constant that will be given to you. Sorry, the constant has no units. Then we can easily find the H concentration just by dividing. 1 times 10 to the negative 14 divided by 1.5. This is a concentration, so I will give it the units molarity. And is that a lot of hydrogen? No, it's a relatively small amount. Remember, water has 1 times 10 to the negative 7 molar concentration of hydrogen, and this number is much smaller than that. So this does not have a lot of hydrogen. It's not acidic. It would be considered basic solution. Try item C and tell me if it's acidic, basic, or neutral. It's more convenient to talk about these numbers as whole numbers rather than in scientific notation. So scientists have invented the potential scale for hydrogen. On the potential scale, we can turn hydrogen concentration into pH with this simple equation. We will practice some in just a moment. But let's look at the pH scale and how practical it is. So to your right, some key features that you need to memorize about the pH scale is 1, a neutral pH is 7. Any pH below 7, including 6.9, all the way to 0 is considered acidic. and any substance with a pH above 7, including 7.1, all the way up to 14, is considered basic. It's a good idea to have a sense of some common things that tend to be acidic or basic, things like maybe lemon juice or coffee, or of course, hydrochloric acid, and some things that are basic. Maybe you've heard of baking soda, bleach. In fact, the acid in your stomach is hydrochloric acid, and if you eat very acidic foods and have acid reflux, one of the treatments would be to eat a spoonful of baking soda. So, since pH is more useful than H concentration, let's practice making a change. So let's look at solution C, where they give us H concentration, but we want to find pH. So we're going to use our calculator, type the negative button, the log, not the ln, and then the given molarity. There are no units for pH, whereas molarity was the unit for concentration. So the pH here is 1.57. Notice this number wasn't even in scientific notation, because if it had been, it would have been 2.7 times 10 to the negative 2. That's a really big concentration. So it has a lot of hydrogen ions, a large concentration, and since we're taking the negative log, we get a small or a low number for pH. So again, things on the pH scale are acidic because they have a high hydrogen ion concentration. That's sort of backwards. Big concentration, small pH. Low concentration of hydrogen or high hydroxide concentration, then a high pH is the result. These equations will be given to you on a test or quiz, and they're very fun. Let's try another one. Since pH plus pOH equals 14, if I know the pH is 1.57, and together they equal 14, then the pOH must equal 14 minus. And finally, if I need to calculate the OH, I have several methods that I can use. I can use my H and the equation for H and OH concentration. I can use my POH and work backwards with the negative log concentration. Let's try that. That one's fun. POH is negative log. In fact, putting anything on the P scale means taking the negative log of that thing. So if I have POH as 12, then the negative log of OH can be derived in the following manner. I'll multiply both sides by -1, and that will get rid of the negative sign on the right. Then I'll take the inverse log. That means I'll have to hit the second and log button on my calculator. That is going to look like this on your calculator screen, 10 raised to the power, and then you can plug in the 12.43, negative 12.43. In this case, it is since I'm getting concentration, I need the units, and I only need two significant figures. You might notice the log button reduces a number to the power of its exponent. So if I take the log of something that is 1 times 10 to the negative 13, I get an answer that's very close to 13. Or if I take the inverse log of 13, I get an answer that has 13 as its exponent. So that's how log works. This can help you with the first 2 homework assignments.